the stuff that we cover in chapter 2, you're gonna question, is this really math? Because there's absolutely zero calculations that we're gonna do, and if we do any, it's gonna be late in the chapter. Okay, this is going to be an interpretation, a kind of a learning and understanding of how mathematical statements are written. Okay, and how we read math statements. Okay. How they're written, how we interpret them, and how we apply them. It is the foundation of pretty much every single rule that is written in any textbook, any math textbook, and most of your science textbooks throughout all the curriculum. Okay, so I take the entire mathematics field, which is huge. Every single rule in there can be brought back to what we learn here in 2.2 and the structure of it, what we learn here in 2.2. Okay, and we're going to start with a lot of statements that are non-mathematical for you to get kind of a grasp of it, and then we'll convert tomorrow into mathematical statements. But it's called conditional statements. Okay, and I know some of these words got cut off when this merged over to a OneNote, but this word here is conditional. All right. So a conditional, and I don't like Pearson has a weird, they're not weird, I mean, this is what a lot of textbooks have, but it's not very insightful. They call it an if-then statement. Okay, but what it really means is that it's a statement that links two parts, two statements. And the second part cannot be met or cannot be concluded until the original part is satisfied, or the first part is satisfied. Okay, that's kind of the structure of an if-then statement. We'll get into great detail about that structure with examples. It'll make a little bit more sense. But a conditional, you guys have all met conditional statements. You've probably met a lot of them today. Okay. If it's 8:30, then it's first period, right? Okay. If it's 9:13, then the bell rings, right? Okay. Our entire schedule is set up on conditional statements. If this happens, then this needs to happen. Okay. Your computers, you guys are using your computers. Okay. Like everything you set up with your computer, all of the interactive stuff that you do. My computer is programmed to know that if the user clicks this little tab right here, then computer do this operation. Does that make sense? Okay. These are all conditional statements. Okay. Every calculator, every phone, every technology piece or device that you use is programmed with conditional statements. Okay. We go through conditional statements in everyday life all the time. My daughter yesterday wanted to go to her grandma's as bad as she's ever wanted to do anything. But she had to meet one condition to clean her bedroom before she'd go. If you clean your bedroom, Lila, then you can go to grandma's. Does that kind of make sense? So we didn't go to grandma's until she was done cleaning her bedroom. And those are conditional statements that you guys see and interact with every day. Mathematics is structured that way. The entire system is structured that way. Okay. Inside a conditional statement are two parts. They're called the hypothesis and the conclusion. The hypothesis is the part following the word if. Okay. So I said if you clean your room. Okay. So that is our hypothesis. If you clean your room. Okay. The conclusion is the part following the word then. So I told her then she can go to her grandma's. Okay. The only way that we can get to a true conclusion, only way that she could get to her grandma's was if she met the first requirement in the if statement, that she cleaned her room. Does that make sense? Okay. And everything in mathematics is that way. Every single thing that we go through, we have to have a particular hypothesis being satisfied before we can reach our conclusion. All right. Now, because there are so many, there's an infinite number of if-then statements that we can make, okay? And we like to talk about them in general, okay? A lot of times we say we talk in generalities. I don't want to have a specific if statement, and I don't want to have a specific then statement. So what we do is we use these little variables P and Q. And P represents all the statements like if you clean your room, or if it's 8:30, or if it's 9:13, or things like that. Does that kind of make sense? So that P phrase stands in for all of the hypotheses that we could ever come across. Okay? The Q stands in for all the conclusions that could be possible. Okay? So it stands in for then the bell rings, or then we go to our next class, or then we eat breakfast, or then we go to your grandma's house. Okay? Q represents all the infinite conclusions that could be written. Okay? Now, a couple different notations here. When you see that symbolism right there, that symbolism means if P, then Q. Okay? A little arrow right there sets that structure up. Okay, another way we read that is that P implies Q. Okay, implies. So if I say, let's say that, let's say today was Thursday, and I'm like, man, guys, tomorrow's a short day. We haven't had a quiz in a while. I need some grades. I need an assessment. If I were you, I'd be really, really, really aware of that. What am I implying? Quiz next day, right? Okay, I didn't come out and say it, okay, but I'm implying it. And that's kind of what this means here, is that this statement here is implying this conclusion. Okay, so that's the structure of that. We can see Venn diagrams every once in a while, okay? But the Venn diagram of a if-then statement, it's kind of a cruddy picture, so I apologize for that. But your P, okay, which is your hypothesis, is going to be fully encapsulated inside the conclusion, okay? And that's the only way that we get a true statement with these conclusions, or these conditionals, is if I choose a point that is inside here that meets the hypothesis, therefore it will meet the conclusion. Okay? Any point that's inside that little circle P, any statement in there, will then satisfy the conclusion. Okay? And we'll talk about that, and it's easier to see the Venn diagram, understand the Venn diagram when we have specific examples. So we'll see some of that here in a little bit. All right. You see the little phrase here. It says the Venn diagram above illustrates how the set of things that satisfy the hypothesis lies inside the set of things that satisfy the conclusion. Like I said, specific examples will make more sense. Okay. One thing, and this was already written in the above slide, but when you're in Math Excel, there's, and this is just mathematics in general, there's strict rules. The hypothesis does not include the word if. If is the identifier for where the hypothesis is. The word then is not part of your conclusion. It's just an identifier to tell you when the conclusion starts. It's the next word. Does that make sense? Okay. So if and then are identifiers. They are not part of either the hypothesis or the conclusion. All right, so here are some examples of if-then statements, okay? It says, if it is a right angle, then it is 90 degrees. That is something that we know, right? Okay. Now, here's the argument. And this is how math exists and how we operate within it. If I give you an angle and it matches that right there, If I give you an angle and it matches that statement, what can you say about the angle that I gave you? Let's say I give you this angle right here. And I put that right there. What kind of angle did I just give you? What kind of angle is angle A? So you can make sure, you can say, well, okay, I have in front of me a right angle. Now what's the conclusion that you can make about that right angle? It's 90 degrees. Okay? Now that's a definition, and we'll talk about definitions later on. But that's how we work with if-then statements. Okay? If I gave you this angle, and I say it's 30 degrees here, okay, does it match that right there? I know using colors here that don't really work well in front of you guys. Does that match that statement right there, 30-degree angle? No. So then I didn't meet that hypothesis, so I'm not even going to look at the conclusion. I'm not even going to look at the then part because I didn't meet the hypothesis. Does that make sense? Okay. So if it is 90 degrees, then it is a right angle. Okay. If it is 90 degrees, then it is a right angle. Would you agree with that? If I told you you have an angle here, so in front of you, I give you this, put 90 degrees right there. Okay. Could you tell me that that angle right there allows you then to make that argument? Right? Okay. So what I want you guys to understand, the way I always view this, is I can only interpret the situation and apply the then statement to my situation if the if part is laying in front of me, and that's what I'm starting with. Okay? So I'm going to go back real quick. You guys don't have to write this down. I'm going to jump back to chapter 1 real quick because we've seen this. So our postulate here, and we can go through all our postulates, but it says if 3 points A, B, and C are collinear, then B is between A and C. So that's our if statement, right? If that's the image happening in front of us, where we've got A, B, C, then we can make this conclusion right there. Does that make sense? Okay. Do you remember when I gave you something like this, said A was there, B was there, and maybe C is up there? Do you remember us saying that we couldn't do that? Because that image in front of us of those 3 points A, B, and C, do they meet the if part? No, they don't satisfy the if part, so I can't apply then the conclusion here for these 3 points because they are not meeting the condition that is set inside the green here. Okay? When I told my daughter yesterday that she could not go to her grandma's, okay, because she didn't clean her bedroom, I said, if you clean your bedroom, then you can go. The condition I gave her was that she had to clean her bedroom, right? Okay? She had to meet a condition. Okay, so this example here says, are if-then statements reversible? Okay, and then there's a question, if you say yes, then the question is, well, are they always reversible? Are they never reversible? That type of thing, okay? So when statements are reversible, let's say this. Let's say I write a statement over here that says, if it is raining and the ground is wet. Would you guys agree that that's true based on what we basically know about rain? All right, so let's say that's true. Let's reverse it. If the ground is wet, then it is raining. Now, when I ask if that's true, I'm asking, is it a universal truth? If I know the ground is wet, does that mean that every single time the ground was wet, it had to be raining? No. Okay, so that we can find excuse me, what we call a counterexample to that. Okay, just something that shows that it's false. It could be true. I mean, if the ground is wet, it could be raining. Right now, the ground is wet out there. It's been raining. Okay, so that's an example of it being true. But 2 days ago, I woke up, the ground was wet, and it wasn't raining because there was dew on the ground, right? Okay. So there are dew on the ground would be a counterexample that shows it false. So that shows that statement was not reversible. What we did here with the right angle, hopefully that shows you that the statements are reversible in that situation. So sometimes if-then statements are reversible, okay? The number one thing that gets people in trouble is that they want to reverse them all the time. They think that everything written in a math textbook is reversible, and it's not, okay? In a math textbook, the way if-then statements are written are to be interpreted just that way, just the direction they're written, okay? If they're reversible, there will be notation, there'll be words in the phrase that tell you they're reversible, okay? One thing to think about, all definitions are reversible, okay? All definitions are reversible. You guys have done this before. You've taken tests where I give you the word and you have to write the definition, right? Okay? But you've also taken tests where I've given you the definition and you just got to write the word, correct? Okay? So that idea, that concept is the fact that they are reversible, okay? And we'll talk about definitions in great detail here in the next couple of days. If two distinct lines intersect, then they do so at one point, okay? That is a if-then statement that we've talked about. That was one of our postulates, right? Okay? If two distinct lines intersect. So you know in front of you, that's the picture I should be thinking about, okay? Two lines that are different intersecting. Okay, if that's happening, what is the conclusion from that? What do I get from that when that happens? And I get the idea that they do it at one point. Okay, if two planes intersect, then they do so at a line. Okay, so those are all statements we've already seen in chapter 1. But every mathematical concept that you've learned from the first day you were doing math to now and beyond, okay, as far as you go with your math careers, every single rule is written as an if-then statement. Okay. Finding counterexamples. Okay. So a counterexample says that it is an example. It is a statement that shows that a conjecture is false. Okay. That shows an argument is false. Okay. So I've got a conditional statement here. It says if for all real numbers x, then the expression x squared is greater than or equal to x. Okay, so it's a mathematical question of where we're trying to determine, is this a fact? Okay, because if it's written as a if-then statement in a textbook, in like the notes of the textbook, it's assumed to be a fact. Does that make sense? We're trying to say, would this ever be written as a fact inside a math textbook? So let's kind of go through some ideas here. It says, for all real numbers x, then the expression x squared is greater than or equal to x. So give me a number for x. 2. So when I go x squared, that would be 4, right? Was 4 greater than or equal to 2? Okay, so that works. So here's the thing. It is when I'm trying to test a counter or find a counterexample or test the validity or truth of an if-then statement, it's good to be able to find a bunch of scenarios that it's true for, but you might have an infinite number of statements that it's true for, and you might have one that it's false for. That one that it's false for kind of contradicts or eliminates all the truths of the infinite truths. Does that make sense? Okay. I always use the idea that I could be, we did this in stats the other day, so I'm like 1,300 days old. Okay, we were doing an age thing, so it's not that I know that just because I'm weird, but we were doing an example, and I had to put my age in days. So I'm like 1,300 days old. If tomorrow I go out and commit a felony, okay, on my 1,301st day, okay, that makes me a felon, right? And that doesn't go away ever. It essentially contradicts the fact that I was a good person for 1,300 days. One action, now that contradicts or eliminates all those good days. Does that make sense? And I'm known now as a felon forever, okay? Same idea here, okay? You can have an infinite number of places that it's true, but one place that's false makes the whole thing false, okay? You've heard the, one bad egg type expression, right? Okay? That's what a counterexample is. Can we find that one bad egg that makes a statement false? So if I try 2, that's true. What if I try like 3? Square that, I get 9. Is 9 bigger than or equal to 3? Yeah, what if let's try a negative number. Let's go -5. Square that, I get 25, right? Is 25 greater than or equal to -5? Yeah, so I'm getting a lot of truths here. What about 0? Because I've tried positive numbers, now I've tried a negative number. Let's try a 0 is referred to, just depending on how you want to use it. Sometimes it's referred to as non-negative. Sometimes it's referred to as non-positive. Okay, it's just the way that you want to deal with it. But if I square 0, what do I get? 0. Is 0 greater than or equal to 0? Yeah. What if I tried like 1? I get 1. Is 1 greater than or equal to 1? Same thing happens with -1, right? -1, square that. I get 1. Is 1 greater than or equal to -1? Yes. So it seems like we're getting a lot of yeses here, right? Running out of examples, running out of values for x. But there are some values of x that we haven't chosen yet. Anybody have a value of x or a type of number that's not been chosen up there for x? A decimal, okay. So let's try, so if I try like a decimal like 2.5, and I square that, so that's my x, I square that, that gives me 6.25. Is 6.25 bigger than or equal to 2.5? Okay, so that was okay. So those decimals. Okay, so if I choose an irrational, let's go like radical 3, which is approximately like 1.7-ish. Okay, if I square that, it gives me 3. Is 3 greater than or equal to 1.7-ish? So that's a good thought. Okay, so 0.25. So let's do that. So I'm going to write it as a fraction. 0.25 would be 1/4, right? If I square that, I get 1/16. Okay? Is 1/16 greater than or equal to 1/4? Nope. Okay? There's my counterexample. Do you see how we had a lot of examples that were true, but find that one counterexample? Now, there's a lot. It's actually, all my counterexamples are the numbers between 0 and 1. Okay? Non-inclusive, meaning I'm not going to include 0, I'm not going to include 1. We've shown that those do show it to be true. But any number between 0 and 1, when I square it, its amount becomes less than what x was. Okay? So those are my counterexamples. Even though there's an infinite number of values between 0 and 1, there are more examples up there that show the statement true than there are that show it false, right? Finding counterexamples can be difficult, okay? But the nice thing about it is you only have to find one. Improving a statement to be false is so much easier than proving a statement to be true. Proving a statement to be true, we have to go through the logic that basically guarantees and shows our audience that there is absolutely no counterexample that can be found. Okay? Have you guys heard of classmates, peers that have taken geometry talk about proofs? No? Okay, so maybe proofs are a process that we go through to guarantee that a statement is true, and it's always true. It basically eliminates all the potential for counterexamples. Okay? We like to talk about conditional statements and whether they are true or they are false. Okay? So you can obviously you can make any conditional statement you want to. You start with the word if, put in some statement, could be complete garbage, doesn't matter. Put comma, then the word then, and then another statement, and it could be, again, complete garbage, and you've made an if-then statement. Okay? And we want to talk about whether it's a true statement or a false statement. We call that the truth value. Okay? If you are in, like, is anybody like computer program or anything like that? Okay, so you got binary or zeros and ones, right? Okay, so with conditional statements inside, like computer programming, these attach themselves to 0 and 1 for true and false. Okay, basically zeros and ones are like opening a switch back on and off, and that's really what's going on with the truth value. Okay. It says in order to show a conditional is true, you need to show that every time the hypothesis is true, the conclusion is also true. So every single time that I see maybe that points A, B, and C are collinear, then I'm able to show every single time that AB plus BC equals AC. Okay? Or every single time that I see that two lines cross each other, then I need to be able to show that every single time that happens, they produce 1 point, or they intersect at 1 point. Okay? Or every time that the ground is wet, I need to be able to show that that means then it was raining. Okay? And we know with some of those statements that you can't do that, so that means that those statements would be false. So to show that conditional is false, you must find at least one counterexample. That's all you need, one counterexample for which the hypothesis is true and the conclusion is false. So you guys said when there is dew on the ground. Okay? If it is raining or if the ground is wet, then it is raining. Well, one counterexample is dew on the ground. That dew on the ground, that example, tells me that the if the ground is wet, then it is raining statement is a false if-then statement. Okay? An infinite number of truths are ruined by one false. Statement may be true almost everywhere you look, but if there is at least one place that it is false, we consider the entire statement false. Okay? I think I'll let you, this is the definition for a counterexample, so I'll let you write that down. You don't need to write that second bullet down. The counterexample is an example that shows that an argument is false or incorrect. So some of you, like, if we were to think like mathematically in everything that we do, I can make the argument that we might have student A who is an A student. My student is an A student, okay? But they might come in on a particular day, take a test, take a quiz, whatever, and get a C on it. If we're thinking mathematically speaking and talking about that statement, if they are student A, then they are an A student. They got a C on something, that's a counterexample. They are no longer able to mathematically be considered an A student. Does that make sense? Now, later on, they might average things out, and, an A and a C might, cancel each other out, but we are going for the idea that it is always meeting that one true hypothesis to be able to use in that conclusion, or to gain that conclusion. The negation of a statement, you guys do this in English, okay? And a lot of times you're going to hear me make comparisons about math to English, okay? Because they're both essentially the same thing. They're both systems of rules that you need to abide by to accomplish something, okay? So the negation of a statement P is the opposite of the statement, okay? So if I have a statement that says, if it is raining, then the negation would be, if it is not raining, right? Okay? So negation just means putting the word not in, creating the opposite, okay? Here we say, if you say the water is cold, the negation would be the water is not cold. Okay? Now, because the way you think, based on your experiences before math, if I say the water is not cold, you might instantly think it's got to be hot, right? Well, there are varying degrees, essentially, of hot or not cold, right? So if I say it's not cold, it could be room temperature. Okay, that doesn't mean it's hot, right? Okay, it could be hot. It could be boiling. Okay, so there's different. So when I say something is not cold, you don't make the jump or the conclusion that it's completely something else, some other statement. You just know what it is not. Does that make sense? Okay, if you are not an A student, let's say Johnny comes in. Johnny's not an A student. Do you automatically say that they're an F student? No, they could be a B, C, or D, right? Okay, so there's varying degrees. When you say not, it does not make you be able to come up with and kind of delineate down to an argument about that thing. Okay. So you use negations to write statements that are related to conditionals. Each conditional has three other statements that are closely related to the original conditional statement. Okay. So tomorrow, we'll stop here today. Tomorrow, we'll get into this stuff. It will benefit you a lot if you print this off for tomorrow, so you don't have to write all that stuff. You can just write little tiny notes on that stuff. Yes. Yes.